Lam, and this is Lab 1, Constant Velocity. Here's what today's video will cover. So, the objective of this lab was to demonstrate Newton's laws of motion in real life by comparing the observed position of an object that travels at constant velocity to the predicted position generated from a computational model using tracker and glow script. Newton's first law states that an object in motion will remain in motion in the same speed and direction, which is also known as constant velocity, unless acted upon by an outside force. Newton's second law states that the net external force is equal to the change in momentum of a system divided by the time over which it changes. From this, we can derive two very important equations. For the velocity update formula, if the net force is 0, it cancels out the second half of the equation, making the final velocity equal to the initial velocity, which helps us prove constant velocity. For the position update formula, we can see that the new position is a result of adding the initial position plus the average velocity times the change in time, where average velocity is the same as the initial velocity. So, since we are studying constant velocity in this experiment, the observed position results of our object are very similar to the predicted position. However, there's a slight deviation which we will discuss. For my experiment, I recorded a video of my can rolling across my floor. Then, I used Tracker to analyze the video to get its observed position in each frame over time. Then, I generated a computational model in GlowScript based off of the data extracted from Tracker to produce a predicted position of the can. Finally, I compiled the data from Tracker and GlowScript to create a spreadsheet and graph to easily compare the observed versus expected position. This is my video being analyzed in Tracker. My system is the can and the surroundings are everything else that interacts with it, such as the ground or any forces. The red dots as the can moves are the center of masses that I manually inputted frame by frame. I had about 40 data points. As you can see, it takes us and compiles a table and graph of the observed position relative to time. Using the Tracker video, we can extract data that helps us set our initial conditions for the computational model. When the time is 0, the position of the center of mass of the can is 0.008425 meters, which gives us our initial position. Then we can calculate the initial velocity given the second data point to give us a velocity of 0.91924 meters per second. The time between frames in the video was 0.033 seconds, so the positions in Tracker were given in these intervals. The entire sequence I analyzed took 1.267 seconds. Next, I took the starter code and changed it as needed, as shown by the arrows, to be a comparable model to my observed conditions. I changed the initial conditions according to my observed initial velocity and position. The delta was my change in time, which was 0.033. Using the equations I derived earlier, I used the variables given in the code to make position and velocity update formulas in a calculation loop, which ultimately let me see the predicted position of my object as time increased and resulted in a positive slope. Here's a video of my computational model being run. As you can see, it resulted in a positive slope as position increases linearly over time. The velocity stayed the same throughout, and the code printed times associated with the positions for me. After getting the observed versus predicted data points given to me in Tracker and GlowScript, I was able to produce a graph comparing the observed position in red to the predicted position in blue. This tells us that in the very beginning, the observed and predicted positions were the same, but as time goes on, the observed position begins to diverge. We would expect it to be perfectly linear like the predicted, but since it diverges, we can assume that there are some outside forces acting upon it which slow it down. This is because the velocity has changed and is no longer constant, meaning net force is no longer 0. So, some possible sources of error are in Tracker, I had to manually choose the center of mass and then manually set the axes, which could slightly cause differences if the center of mass isn't perfectly accurate every single time. And then, like I mentioned, there are some outside forces that we didn't account for, which affect the observed positions, maybe such as friction. And then also the camera angle of my video in Tracker, it's slightly, it might be slightly slanted towards the end, which could affect the center of mass, which could affect the position. So, what if the axes were flipped, such as instead of going in the plus x, it went in the minus x? The only difference would be that the slope/velocity would be negative, since it would be going in the minus x direction instead of the plus x direction. But ultimately, it would not change the physics concepts behind it. And is it possible to say how many pushes and pulls are added together to give the 0 net force? I cannot determine exactly how many individual forces are acting together to give a net force of 0 just by looking at the object's motion. We know that if no other forces were acting on it, then the normal force and the force of gravity would cancel out to give us a net force of 0. However, since the observed model eventually deviates a little from the predicted model, there must mean that there are other forces acting on our system that we can't determine. Thank you for listening.